Welcome. Let's journey back in time, not too long ago, to a world where every great invention, every towering skyscraper, and every intricate machine began its life on a drafting board. Imagine architects and engineers hunched over large sheets of paper, armed with T-squares, compasses, and pencils. Every line was drawn by hand, every revision required painstaking erasure, and every copy was a manual, often imperfect process. This was the world of manual drafting, a world of incredible skill, but also one of significant limitations in terms of speed, accuracy, and collaboration. Then came a revolution, a paradigm shift that would forever change the face of design and engineering: computer-aided design, or CAD. CAD is not merely a digital version of the old drafting board, it is a fundamental reimagining of the entire design process. It replaced the physical tools with a virtual environment where ideas could be brought to life with unparalleled precision. This transition from analog to digital unlocked new dimensions of creativity and efficiency, allowing designers to create, modify, and analyze their work in ways that were previously unimaginable. It allowed for complex calculations to be performed instantly and for designs to be shared and collaborated on across the globe. This introductory slide sets the stage for our exploration of CAD, a technology that moved design from the constraints of paper to the limitless potential of the pixel, laying the foundation for the modern world we see around us today. Every revolution has its pioneers, and in the world of CAD, the story begins in 1963 at MIT with a PhD student named Ivan Sutherland and his groundbreaking thesis project, Sketchpad. It is hard to overstate how visionary Sketchpad was for its time. In an era of punch cards and room-sized mainframes, Sutherland created a system where a person could use a light pen to draw and manipulate geometric figures directly on a screen. You could draw lines, set their lengths, and even create copies. If you changed a master line, all its copies would change automatically. This was the birth of interactive computer graphics and parametric design, the very DNA of modern CAD. For many years, however, this technology remained the exclusive domain of large corporations in the automotive and aerospace industries, running on expensive, specialized hardware. The true democratization of CAD arrived with the personal computer. In 1982, a small startup named Autodesk released a program called AutoCAD. By running on affordable PCs instead of costly mainframes, AutoCAD put the power of computer-aided design into the hands of small businesses, independent architects, and individual engineers. This was the tipping point. AutoCAD's accessibility and robust feature set made it an industry standard, accelerating the retirement of the drafting board and firmly establishing digital design as the new professional norm. Opening a modern CAD program for the first time can feel like stepping into the cockpit of a sophisticated aircraft. The interface is meticulously organized to provide designers with maximum control and efficiency. Let's break down this digital workspace. The heart of the interface is the infinite drawing area, your virtual canvas where ideas take shape. It can be a 2D plane or a 3D space. Along the top, you'll typically find the ribbon or toolbars, which logically group hundreds of commands, from simple line and circle tools to complex 3D modeling functions. For power users and those who prefer keyboard input, the command line is a crucial element. It allows for the direct entry of commands, coordinates, and dimensions, enabling incredibly fast and precise operations. At the bottom of the screen, the status bar acts as your instrument panel, providing real-time feedback and access to critical drawing aids like grid snap, ortho mode, and object snaps, which ensure perfect alignment and accuracy. Finally, a key concept to grasp is the separation between model space and paper space, accessed via the Model and Layout tabs. Model space is where you build your design at 1:1 scale. Layout tabs or paper space are where you arrange, annotate, and scale your design views to prepare them for printing on a specific sheet size. This entire ecosystem is designed to work in harmony, creating a powerful and intuitive environment for digital creation. At its core, what does CAD software actually do? Its capabilities are vast, but they begin with the fundamentals of 2D drafting. This is the process of creating the flat, technical drawings that serve as the language of engineering and architecture, floor plans, schematics, and mechanical part details. CAD allows for the creation of these drawings with absolute mathematical precision. But the real power comes from moving into the third dimension. With 3D modeling, designers can transform flat drawings into tangible virtual objects. They can create solid models with volume and mass properties, or intricate surface models for aesthetic and aerodynamic designs. This leap to 3D allows for visualization from any angle, interference checking between parts, and the creation of realistic renderings. Underpinning all of this is a suite of powerful tools that guarantee accuracy. Parametric constraints, for example, allow you to build intelligent relationships between parts of your design. If you change the length of one wall, the entire room can automatically adjust to maintain its proportions. Object snapping ensures that your new line connects perfectly to the midpoint of another or the center of a circle. Beyond drawing, CAD is a platform for efficiency. Repetitive tasks like creating a specific type of bolt or annotating dimensions can be automated with scripts. Furthermore, application programming interfaces or APIs allow companies to build custom tools and integrate the CAD software directly into their unique workflows, making it a truly adaptable and indispensable tool.
The true testament to CAD's power is its ubiquity. It has become a universal language of design, spoken across a vast spectrum of industries. In the architecture, engineering, and construction (AEC) sector, CAD is the bedrock. Architects draft precise floor plans, elevations, and 3D building models. Engineers overlay these plans with mechanical, electrical, and plumbing systems, using clash detection to ensure pipes don't run through structural beams before construction even begins. This culminates in Building Information Modeling (BIM), where the CAD model is an intelligent database containing every component of the building. In the world of manufacturing, CAD is equally indispensable. Mechanical engineers design everything from a simple nut and bolt to a complex jet engine assembly in 3D. These digital models are then fed directly into computer-aided manufacturing systems, which control CNC machines to mill the parts with perfect accuracy. It's also the first step in rapid prototyping, where a 3D model is sent to a 3D printer to create a physical prototype in hours. Beyond these, the applications are endless. Electrical engineers use specialized CAD tools to lay out intricate printed circuit board schematics. Civil engineers use it to model terrain, design roadways, and plan massive infrastructure projects. Even fields like entertainment use CAD for set design and visual effects. This versatility demonstrates that CAD is not just a tool, but a flexible platform that adapts to the unique challenges of any design-focused industry. Why did CAD so completely and utterly replace the drafting board? The answer lies in a set of tangible, game-changing advantages. First and foremost is accuracy. A line drawn in CAD is not just a representation, it is a mathematically perfect entity. The software eliminates the minute human errors in angle, length, and alignment that were unavoidable in manual drafting, leading to higher quality products and fewer construction errors. This precision leads directly to the second benefit: efficiency in time and cost. Modifying a design is no longer a process of erasing and redrawing. It's a simple command. Designers can explore dozens of iterations in the time it would have taken to create one manual drawing. This speed translates directly into reduced labor costs and faster project completion times. Third, CAD brought about standardization. It allows companies to create and enforce consistent documentation standards from line weights to text styles. More importantly, it facilitates adherence to global industry standards like ISO and ANSI, ensuring that a blueprint created in one country can be perfectly understood and manufactured in another. Finally, modern CAD has revolutionized collaboration. With the integration of cloud platforms, team members from different offices or even different continents can access and work on the same master model in real time. This eliminates version control nightmares and fosters a more integrated, communicative, and efficient design process. These four pillars, accuracy, efficiency, standardization, and collaboration, are why CAD is not just a tool, but the undisputed industry standard. While the core functions of CAD have remained consistent, the technology is in a constant state of evolution, pushing the boundaries of what is possible. Today's advanced CAD software offers capabilities that sound like science fiction. Beyond simple 3D shapes, designers now utilize a trio of advanced modeling techniques. Solid modeling creates objects with volume and physical properties, ideal for engineering analysis. Surface modeling allows for the creation of flowing, organic, and aesthetically complex shapes, crucial for automotive and product design. Mesh modeling provides the flexibility to sculpt and mold forms as if they were digital clay. But the innovation isn't just in creating shapes, it's in making the workflow smarter. Dynamic blocks are intelligent, reusable components that can be stretched, rotated, or reconfigured on the fly, saving enormous amounts of time. Sheet sets provide a powerful way to manage and publish large multi-drawing projects as a single organized unit. Perhaps the most exciting frontier is the integration of artificial intelligence. AI-assisted drafting can predict a designer's intent, suggesting commands or automatically cleaning up geometry. Taking it a step further is generative design. Here, the designer inputs a set of goals and constraints, such as material, weight, and strength requirements, and the AI algorithm explores thousands or even millions of design permutations to generate optimal solutions that a human would never have conceived. These advanced features show that CAD is evolving from a passive tool into an active and intelligent partner in the design process. As we look to the future, CAD is solidifying its role not just as a design tool but the central hub of a fully integrated digital ecosystem. The boundaries between the digital model and the physical world are blurring. Integration with virtual and augmented reality (VR/AR) is a prime example. Imagine an architectural team no longer just looking at a model on a screen but putting on headsets and walking through their building at full scale before a single brick is laid, spotting issues and refining the user experience in a truly immersive way. The connection extends further with the Internet of Things. By embedding sensors in a physical product or building and feeding that data back to its digital CAD model, we create a digital twin. This allows for real-time monitoring, predictive maintenance, and performance optimization throughout the object's entire life cycle. This seamless flow of information is the core idea behind building information modeling and computer-aided manufacturing, which directly link the digital design to construction logistics and automated manufacturing processes. Ultimately, all these integrations serve a greater purpose. By creating a continuous thread from initial concept to real-world operation, we can design more intelligently. We can optimize for energy efficiency, reduce material waste, and build more sustainable products and infrastructure. The future of CAD is not just about drawing faster, it's about making smarter data-driven decisions to build a better, more efficient, and more sustainable world.